Hello, this is Kiyomi. I go by my middle name Denise. This study was carried out during my time at University of Bath back in 2018 for my dissertation, which has produced some interesting findings that we'd like to share. I'm currently working at a facade specialist company, but would really like to go back to research more on moisture buffering someday. So let's get on with the presentation. Modern buildings are designed to be well insulated with minimum infiltration to reduce heat loss. While indoor relative humidity, RH, is conventionally controlled by air conditioning units, such systems have been shown to be inadequate to bring indoor RH to the optimal level in certain cases and require additional energy consumption and associated environmental impact due to their operation. High indoor RH also requires more energy to heat up the air with high specific heat capacity of moisture, further increasing energy consumption when compared to heating air in a low indoor RH environment. Occupant interaction with mechanical systems play a vital part in energy and carbon performances of buildings, as well as regulating the indoor air quality. Studies have reported the merit of having hygroscopic materials within an enclosed space to moderate indoor humidity variation, while others later testified on the positive impact on energy efficiency and occupant comfort. The increasingly apparent global climate shift indicates that there is a rising need for a passive system which would be suitable across all climates. It was not until the past decade when the concept of humidity buffering has started to be actively discussed in the field of building science to control indoor climate, despite being applied since as far back as the 1640s and widely practiced in humidity-sensitive trades, such as the use of silica gel in preserving the artifacts and to prevent moisture damage in military equipment. Hygroscopicity is defined as a substance's tendency to attract moisture from air. Adsorptivity, as opposed to absorptivity, is description of the travel of moisture into the material instead of the material itself soaking up surrounding air moisture. A hygroscopic material, often porous or fibrous with breathable properties, will form a passive moisture buffering phenomenon where air moisture actively travels in and out of the material, depending on surrounding moisture load variation, absorbing moisture during high moisture load phase and desorbing during low moisture load phase to achieve moisture equilibrium with the vapor pressure. In a real room, each piece of furniture and decoration and the capacity of each material, the ratio between the material surface area and the air volume also contributes to the performance of this passive system. To simplify things, the material tested is taken to be homogeneous. To demonstrate the efficacy of moisture buffering materials, the Nord test method, which has been developed by the Nordic countries, is currently the most recognized way to appraise the moisture absorption in materials. A brief look into the round-robin tests conducted across different institutions would require the test setup to be of 8-hour high humidity, which is about 75% RH, and 16-hour low humidity, about 33% RH, under the isothermal condition of 23 degrees Celsius within one test cycle of 24 hours. Due to the nature of these test assumptions, the data collection cycle is also very limited as the moisture uptake and release pattern is restricted by the two-step preset moisture load. It has been concluded that the different tests produce comparable results but only under very specific conditions. As seen in the graphs, the testing condition in the Nord test method does not represent the reality with such controlled environment, and presumably neither do the existing gathered data. It is questionable if the data obtained to determine moisture buffering values could directly be applied in a real-world condition, where there are many other ever-changing environmental factors besides air temperature and RH, such as pressure, with RH being defined as the ratio of vapor pressure and the saturation vapor pressure, moisture load, and air change rate, amongst other parameters that should also be considered to properly study the moisture buffering properties of a material in a practical manner. Under varying RH conditions, moisture will only penetrate into a hygroscopic material to a depth that will vary depending on the material, but for typical plastering material is limited to approximately 10 millimeters. The materials selected for this study are gypsum, a conventional building material, and clay, an earth source material to aid further development in sustainable construction. Two materials were included in the study to observe the diversity of response to justify the feasibility of applying this testing method across different materials. Specimen thickness is twice of the optimal thickness to allow for uncertainties. Before placing the specimens in an environmental chamber with controlled varying conditions, the back and side faces of the specimens were covered in aluminum tape to seal and ensure that the interaction with surrounding air moisture only occurs at one face. A sinusoidal variation curve referencing the step variation with positive and negative RH arches has been created, where high RH is maintained for 8 hours and low RH is maintained for 16 hours. Being inversely proportional to RH, the temperature variation was set to start with an 8-hour negative arch instead. Testing profiles were limited to an ideal condition taken to be 23 degrees Celsius and 50% RH. Temperature variation inversely proportional to RH limited by lowest acceptable temperature of 18 degrees Celsius and maximum allowable temperature for overheating of 28 degrees Celsius. While efforts were made to keep air velocity within the range of 0.02 to 0.3 meter per second, the effect of airflow variation is not taken into account. The tests are conducted with the aid of an environmental chamber with controlled varying condition. Apparatuses used throughout the testing period are 1 temperature and RH logger, 1 climatic chamber, 2 high-precision electronic balances, 2 computer tablets connected to electronic balances for data logging, and 2 screens to keep airflow within range. Test period is set to be 24 hours per cycle, with minute interval data collection to study behavior pattern of the materials under specified condition. 4 types of tests have been developed and expanded to 3 more profiles for each of the temperature and RH variation tests. In general, each test is allocated the time for 2 cycles to obtain feasible data, repeated for 3 specimens for each of the 2 materials. The table is a summary of testing profile where the number of data sets collected are stated in the test description. 3 complete sets of data indicate that there were no data recording error for that specific test, and erroneous tests were repeated to ensure that there were at least 2 complete sets of data. There were slight differences in RH and temperature within the climatic chamber as the actual values could not be maintained exactly as what was being programmed. RH is said to be heavily influenced by temperature, but condition monitoring data showed that RH affects temperature just as much, seeing that temperature could not be kept constant and tends to fluctuate according to both positive and negative peaks of the temperature curve. The resultant temperature has a mean difference of 0.5 degrees Celsius lower than the preset temperature of 28 degrees Celsius, while the resultant RH has a mean difference of 4 to 5% higher than the preset RH. Even though resultant curves are noisy in general, the range of fluctuation for both resultant temperature and RH are especially big when the temperature curve is at its high peaks. This may suggest that low RH will induce a rise in temperature when kept at high temperature condition. Interestingly enough, the statement RH is inversely proportional to temperature no longer applies under low RH condition, as the resultant RH appears to be fluctuating in accordance to temperature change instead. The NORD test is carried out to act as a control set, as it is a standard test procedure with readily available literatures and benchmark data. However, although the obtained results showed a similar trend curve, the gypsum sample displayed a higher moisture uptake amplitude compared to the clay sample, in which preceding literature review would suggest otherwise. While more results will be needed to justify findings for accurate comparison, the different composition of the clay samples, which also consist of silt, may be the main cause of this unprecedented results. The analyzed test results are limited to one single complete sinusoidal curve, starting from desorption arch in cycle 1 and next adsorption arch in cycle 2. Considering that the beginning of the test would also include factors of the material recovering from its original state before it could get on with moisture buffering, The first adsorption arch may not show consistent results of the material interacting with the environment it is subjected to, while the second desorption arch in cycle 2 is not complete and therefore cannot be used. Each annotation is defined as response offset, time taken to achieve peak uptake or release in response to preset condition, resultant arch period, actual time required to complete curve, adsorption or desorption, moisture uptake or release per exposed surface area, sorption capacity, sum of adsorption and desorption. Looking at average results, the sorption of all clay samples peak at the same time, exhibiting synchronized delay in response to RH variation peak points. Higher temperature yields a greater amplitude of sorption, while lower temperature generated a similar moisture uptake and release. Gypsum specimens displayed similar curves. It is suggested that higher temperature would induce higher moisture adsorption and desorption, while the margin of difference in resultant moisture uptake and release may not be directly proportionate to the change in temperature. Results obtained for clay specimens would produce a less apparent but similar trend. Negative response offset is observed in temperature variation tests as opposed to the positive offset seen in RH variation test. This may be caused by the fact that the material could not retain moisture uptake at low temperature, especially when high temperature is brief and focal instead of being constant and perpetuated. Both materials start to release moisture even before reaching peak temperature, but this situation evidently improves with increase of RH where positive offset have been recorded during the desorption process. With the temperature change ratio being 1 to 1.25, none of the resultant adsorption and desorption ratio are equivalent to the ratio in temperature change, where almost all cases resulted in more than twice the sorption capacity at higher temperature when compared to low temperature. The case is similar for the ratio of RH change of approximately 1 to 1.5. While the results obtained for clay materials posed a possible relationship between margin of change in condition and margin of resultant sorption capacity, other cases may suggest otherwise. Compared to clay specimens, gypsum specimens appear to adsorb and desorb moisture at a faster rate, resulting in a greater sorption capacity. It is assumed that although the clay specimens may be slightly inferior in sorption capacity, their excellent moisture retention capacity results in their consistent behavior and how they respond to the change in external condition. The increasingly spread out results as temperature increases could suggest several unforeseen factors, with one of them being the decrease in performance stability in the material itself. Previous literature suggests that clay performs better than gypsum in terms of moisture buffering, which has not been observed here. Gypsum, having higher sorption instead in this study, could imply that the sorption capacity in clay deteriorates over time, potentially due to clay specimens having managed to get closer to moisture equilibrium through continuous moisture retention, while also continuing to adsorb and release moisture whenever there is a change in environmental condition. The estimated combined effect of sinusoidal variation of RH and temperature can be estimated numerically. To ensure comparability, the data obtained from tests at constant ideal conditions at 28 degrees Celsius and 50% RH respectively have been used to predict this resultant curve by the average of the two sets of data. The resultant curve infers that simultaneous variation of both temperature and RH will reduce the sorption capacity of the material, as well as a further delay response time indicated by response offset. Removing ideal condition altogether, the combination of hot and dry condition appears to make full use of the material's sorption capacity, while cold and humid condition results in the sorption fluctuation of the least vertical amplitude. The material's performance appear to be fairly consistent when subjected under cold and dry condition, and the inclination for continual moisture desorption in hot and humid condition is less than hot and dry conditions. This would imply it is best to avoid dependence of hygroscopic materials' moisture buffering ability when designing in a closed space under cold and humid conditions. The combination of cold and dry condition rated relatively well in terms of absorption capacity and response time while being able to maintain performance. The resultant peak point could be a form of absorption balance point, where instantaneous adsorption is equal to desorption. The results obtained in this study shows that the peak points are almost never in sync with the programmed setting, causing an offset in response time. This is a comparable phenomenon to thermal lag. The different combination of high and low temperature corresponding to the given humidity affects the instantaneous adsorption and desorption rate of the material, which governs the shape of the resultant absorption graph. Observing that the test result outcome does not correspond to the profile setting, there could be a possibility where the profile setting itself is not appropriate for fair comparison to achieve a case of similar adsorption and desorption within 8 to 16-hour profile distribution. A change of test profiles in accordance to the function and suitability of each building design, the resultant adsorption might turn out to be equal or at least close to desorption and could therefore better justify the moisture buffering performance of materials. It would also be beneficial to determine a way to shorten the material's response time with reference to the relatively high or low RH level without compromising on thermal comfort and indoor air quality to get a more accurate way to properly predict the performance of moisture buffering materials. To recap, this study has experimentally demonstrated the impacts of RH and temperature variation on various hygroscopic materials' ability to passively regulate the indoor environmental RH. It has changed from a step cure to a sinusoidal curve that has resulted in additional properties that are not typically considered, including rate of adsorption and moisture offset or lag. It has presented numerical results when these variations are combined. The combination of two variations will result in the occurrence of reduced absorption capacity and a delay in response time, irrespective of how high the moisture buffering performance of the material is. Most of all, it has also questioned the long-term performance of moisture buffering material, which is key for consistent performance over a prolonged period of time with minimal maintenance and preferably sustainably sourced. Thank you for your attention.